Hey, let's talk about the mass transfer coefficient and its theoretical foundation. So if you recall, when in the lecture we discussed about the three types of boundary condition, and in the third type of boundary condition, we introduced a concept called the mass transfer coefficient, and we use Km. And this is what we are talking about today. So we will first introduce what is a mass transfer coefficient. So this is, first of all, you can understand it as a proportionality constant. So what does that mean? Let's consider the interface between like a solid boundary, and a fluid containing a dissolved solute species A. So you have a fluid above. The flux of species A in the direction perpendicular to the boundary, let's call it y. So the flux in this direction, it's actually, you can have flux, you don't have to have that start from the plate, but in general. So the flux is given by fixed first law. Means the flux is proportional to its gradient, to the concentration gradient. So if you are asking what happens right on the plate instead of anywhere, then you can say, let's evaluate at the y equal to 0. So in practice, the concentration gradient at the wall or anywhere is not usually known and is difficult to measure or predict. So for this reason, sometimes people instead want to use an approximate but a highly effective representation involve the mass transfer coefficient. So instead, they are saying, okay, let's say what if we can write in this way, the flux zero. Flux equals to a mass transfer coefficient multiplied by the concentration difference between the plate and the bulk. So on the plate, it's CAS. Far away, it is CA bulk. Then it's not necessary to be very much far away. It's as long as it's beyond the boundary layer, you may consider it as the bulk part. So for the CAS, the concentration at the surface, it's in many of the situation in this class, in the later sections, later lectures, you will see it's typically assumed to be known, or sometimes it can be estimated. But however, for this mass transfer coefficient to use this equation, you don't have to know CS. Means you can also solve for CS from other ways if that's needed. So the mass transfer coefficient only meant to tell you that the flux from the plate is proportional to the difference between the concentration on the plate and the concentration far away from the plate. That's why we call it a proportionality constant. Okay, now the concentration difference is the driving force. So this is, let's see, driving force. So if you compare these two, and you may sort of figure out like what Km would be. This is what we are going to use later, how to estimate this. But right now, let's just accept this equation. And so this is flux. This is flux. Flux means it is material. Area, the unit time. So what if you wanted to know the total mass transfer from a surface of area? So the total mass. Well, mass transfer rate from a plate of surface area S. Then we can find the mass rate. We use dot as the mass transfer rate. Then it's basically like mass either gram or kilogram per unit of time. So you can first get the mole per unit of time, and then you can convert the mole into mass. So what you can do is find the flux and then multiply by the area. So the flux is well, this is the area, and the flux is CAS. Or the flux is K multiplied by concentration difference, and then you multiply by the area. It give you mole unit time. And then if you want to convert it into gram or kilogram, then what you just need to multiply it by the molecular weight. That give you the conversion. So that is conceptually what the mass transfer is. So the mass transfer coefficient Km, it appears as a proportionality constant that encapsulates all the underlying physical and geometrical complexities, like including diffusion, flow condition, and the boundary layer development. So it put everything into a single parameter that relates the mass flux to the measurable concentration difference across the interface. The idea is, so practically people use this equation because they have difficulty to find the flux from fixed first law. It's not because the fixed first law is harder to use, but rather it's harder to find the concentration profile as a function of space. Because in order to use fixed first law, you needed to know the concentration as a function of x or y, then you can take derivative. Otherwise, you cannot take derivative if you don't know it as a continuous function. But to use the mass transfer coefficient, you don't need to know everything about the concentration profile. You only needed to know what happens on the plate, the concentration on the plate, which is CS, and the concentration far away, and then somehow suppose you know what is Km, you know the mass transfer coefficient. Then you can know the flux. So that's the idea of doing this. Then you may wonder, okay, how do we know Km? It's in some cases you may be able to derive it. Sometimes it can also be determined from experimental condition if you cannot derive it analytically. Now let's look at an example that people can derive the Km analytically. So the example is find the effective mass transfer coefficient for the unsteady diffusion solute A from a flat plate into a semi-infinite stagnant medium. Okay, so this is the exactly problem we discussed the last time. This is a classical example of unsteady diffusion. So in that case, if you recall from our last lecture, we derived that the flux from the plate is dAd divided by the square root of phi dA multiplied by the concentration difference. So this is if you forget like from last lecture, we can review. Okay, now if you compare this one with the expression here, this equation, because they must be the same thing, because the flux from the plate is the flux from the plate. It's only one value, no matter which expression you use. So if you compare this one, this is how we define the mass transfer coefficient. Now this is the flux from the problem we know. Then you compare it, you can get this is the Km. Or I should say this is the Km for this particular problem, that you have a flat plate and diffuse into a semi-infinite medium. If you have a different problem, you get a different Km. So you can also write it in terms of boundary layer thickness. If you recall, our last time we discussed boundary layer thickness. About 4 times AB multiplied by T 5 times. It's also from last lecture. So if you replace this expression with boundary layer thickness, you will get 4 AB divided by delta C D square root of 1. So this relationship, the new expression involves boundary layer thickness, reveals a critical feature of the mass transfer coefficient in this unsteady diffusion problem. So first of all, we know it is time dependent. Well, the boundary thickness is time dependent. That means the mass transfer coefficient is also time dependent. This is critical. That means the mass transfer coefficient doesn't have to be a constant, or it may not be a constant from the physical process. Yes, it may not be a constant from what it needed to be. Let me complete the writing. Dependent. So as you can see, as time increases, the boundary layer thickness increases. And then it will give you a decreasing mass transfer coefficient with time. This reflects the physical intuition that as the solution penetrates deeper into the stagnant medium, the resistance to mass transfer grows. So the resistance of transfer behavior grows. It is due to the thickening of the region over which the solute must diffuse. So now you can treat the boundary layer thickness as a region of diffusion. Then the thicker the region is, the higher the resistance of the diffusion is, and then the lower the mass transfer coefficient will be. So hopefully this particular example helps you to develop a physical intuition of what this mass transfer coefficient is. And if not, I suggest you just go through this process again, like derive it on your own, and try to connect the different physical relations in your mind, and try to visualize this process in your mind. Like you can draw some pictures of diffusion and draw some boundary layer, and to see how you can digest this process. Okay. Now it leads us to a new unrelated topic called the film theory. So the core idea of film theory is to simplify the diffusion convection problem by assuming the existence of a hypothetical stagnant film adjacent to the surface. So the idea is, as I just said, so you may have a plate, and depending on the scenario, you may have some flow, incoming flow, and then you will develop like a fluid boundary layer thickness. And then within this boundary layer, you have fluid velocity along 2 different directions. And you think about the diffusions, in this case, you would have convection in both X and Y direction. So horizontally and vertically. And then vertically, if you consider diffusion from the plate, you also have diffusion. So now you have a mixture of diffusion and convection. And given, as we also derived, that the velocity profile in this region are pretty involved. It's not like a constant or linear. So that means theoretically it's harder to track all of these. And so that means the resistance to mass transfer is a little bit complicated outside this region. And the scenario is a little bit easier to handle. You may think, okay, outside of this boundary layer, then there would be no velocity along the vertical direction, although there is Vx, but no Vy. And then you can also assume that the things, solutes are fully mixed. And for this reason, we can think about within the frame. Let's consider a scenario that the diffusion is dominate. So the diffusion is the dominant transport phenomenon within the layer. Then the idea is we want to treat everything above the boundary layer as something well mixed. And then we assume within the boundary layer, we assume or approximate is dominated by diffusion. So we are going to write out the mass transfer coefficient in the framework of film theory. So we are saying under film theory, we can write out the mass transfer coefficient as the diffusion coefficient divided by delta film. So delta film is the thickness of the film. And for example, in the above example, I mean, you have a plate that diffuses into a stagnant medium. This is the perfect example. Can have delta film equal to delta C T multiplied by square root of pi divided by 4. So this is what I mean, the above example. So you follow the definition of Km, and that's you can get it. So in some scenario like this classical example of diffusion, you can get an analytical solution. So the film theory, you may ask what exactly it is. It provides a conceptual model that allows us to link the observed mass transfer behavior to measurable fluid and geometrical properties. So it clarifies that the mass transfer coefficient depends directly on the solute diffusion, and the diffusion, like proportional to the diffusion coefficient of DAB, and also inversely dependent on the film thickness. And the film thickness is not a fixed boundary. And you can see in this case, it's also a function of time, but it's a notation, notational like a constructor that represented the resistance to mass transfer. So the if you look at the place the delta film appears, it appears in the denominator. It's still serves as a resistance, and its magnitude depends on system geometries, the physical property of fluid, and the flow conditions, etc. So let's see. We have introduced the idea of film thickness, like the film theory. So the idea of the film theory is to try to get rid of computing the derivatives and like figuring out the contribution from convection and diffusion within those complicated boundary layer. So that's the goal. So the film theory is saying, okay, if you know a film thickness and if you know your diffusion coefficient UAB and then delta, then you can take the ratio and this will be your Km. And once you know the mass transfer coefficient, then you can use our earlier equation to get the flux. And in terms of like how do you know the delta film, it may not be an easy answer. You can derive it in this example, but in a lot of other cases you may not. Then you may ask, okay, if we cannot get a delta film easily, then what's the advantage of using delta film if it's unknown compared to just solving everything from the scratch? It depends on the practical reason. So delta film give us just a conceptual advantage to understand the diffusion so that we can, okay, within the delta film region, it is diffusion dominated. Oh, by the way, when I say this dominated by diffusion along, I mean along the y direction. So this is one. Along the x direction, it's pure in this scenario, it's pure, almost a pure convection. So what I mean is, if you consider the flux along the y direction, then within the boundary layer, or within the thin film layer is dominated by diffusion. So the film thickness is a theoretical simplification. It doesn't mean it's easy to obtain what is delta film. So, but this is the film theory. Okay, let's introduce a new number. It's called the Sherwood number. So the thin film theory, as I mentioned, it introduces a simplification by considering the complex transport process into a single empirical term. It does not eliminate the need for deeper analysis. However, it provides a framework that motivates the use of dimensionless parameters to generalize mass transfer data. So the Sherwood number is one important dimensionless groups in the context of transport. So this, let's define this. What is the Sherwood number? Am is mass transfer coefficient. DAB is the diffusion coefficient of solute A in medium B. What is L? L is not a particular number or anything. It is the characteristic length of the problem. So it's the characteristic length. So what does characteristic length means? So for example, if you have a pipe, what's the characteristic length? It's actually, it's the diameter of the cross-sectional area. That's a characteristic length. If you have a flow over a sphere, then the characteristic length would be the diameter of this sphere. And if you have a plate, then the characteristic length would be the length of the plate. So it depends on your problem. It's not a fixed length for any geometry. And we will show in a later lecture that the showed number will be formulated in other theoretical basis that we like work with other non-dimensional number like the Reynolds number and the new number we are going to introduce. So okay, let's see. I think I haven't mentioned to you what's the meaning of this showed number. Okay, first of all, let me write it down. It is a dimensionless group. The meaning of it is, so whenever you are given a dimensionless group like Reynolds number, now here we have showed number, you always look at what is in the numerator and what is in the denominator. In the numerator, you have mass transfer coefficient, which has units of velocity. And then you ask yourself, at what scenario is this mass transfer coefficient used? It is used when you have sort of a convective transport between from a plate to the bulk region. So it is a proportionality coefficient tell you the flux, how flux is related. It is proportional to the concentration difference. So the physical meaning is the convective transfer above the plate. So it's convective transfer. And in the denominator, well, denominator is a diffusion coefficient. So we know that it's diffusive transfer. So the Sherwood number is a comparison of which transport mechanism dominates. Is it dominated by diffusion or dominated by convection? So this is the number. Okay, now let's look at an example so that we can sort of further digest this lecture, like about the use of mass transfer coefficient and the others. We discuss an example. Okay, so a thin polymer sheet is saturated with a trace gas that gradually dissolves into a Delphian environment. So you can think about we have a sheet, polymer sheet. And you have something dissolve into the vacuum. So this is vacuum. After 7 days, the mass of the gas retained in a 2 centimeter square section of the polymer has decreased by this amount. So this surface area is 2 centimeters squared. After 7 days, this amount of mass is gone. The vacuum shows that the gas concentration in the surrounding environment remains effectively zero. That means you can assume the concentration A in the bulk is zero. That's what this sentence means. So effectively zero throughout this product. This is what the meaning of this bulk. The concentration of the gas at the surface of the polymer is, okay, this tells us what a CAS is, concentration on the surface. The diffusivity of the gas in the polymer is this amount. And the molecular weight of the gas also gives us molecular weight. That's us to estimate the mass transfer coefficient and the effective desorption film thickness. So for this, let's see how can we connect everything together. You have been given the mass decrease, which is 0.052 gram, which is over 7 days. So it tells you the mass transfer rate, M8 dot. And it also gives you surface area, molecular weight, the concentration, to ask you to find the Kn. So now you can think about in your mind, like, what type of physical process relates those properties together? And what you will figure out is this equation. Well, we already discussed this equation. It's not that you created this equation, but you figure out that this is the equation we are going to use. So you have Kn multiplied by S multiplied by CAS. Originally, you have CAS minus CA bulk. Since CA bulk is 0, so you just have CAS. And then multiply by the molecular weight. Now, what is M8 dot? On the other hand, M8 dot is the total mass lost divided by time. So the total mass lost is 0.052 gram. And the total time is, let's say we have 7 days. Each day we have 24 hours. Each hour we have 3,600 seconds. Then you will get your mass transfer rate to be 8.6 times 9 10 to the power of -8. Is gram per second. So now you can obtain your mass transfer coefficient by using M8 dot divided by the area divided by CAS divided by molecular weight. So you put in the number in the mass is next door mass rate is 6 or 8.6 times 10 gram per second. And your area you have 2 centimeters squared. Concentration is 3 into the -9. Then you have molecular weight. It's 98 gram mole So it will give you 0.146 centimeter per second. So this is km. And in terms of like thickness, it also asks us the film thickness. Notice that the km will be DAB by delta film. So we can solve for delta film by using DAB divided by km. So we are given the diffusion coefficient 0.045. Okay. So it's just 0.045 centimeters squared per second divided by 0.146 centimeters per second. Eight millimeter. So this is an example. Hopefully it helps you to digest what is like help you to develop intuition and help you to digest what is km and what is film thickness. Okay. Solutes. Volatile compound is dissolving from a flat liquid surface into stagnant air. The measured mass transfer mass flux is given, and the mass transfer coefficient is also given. Ask you to determine the surface concentration of the compound, assuming that the bulk air contains none of the vapor. Let's see. In the previous problem, we use this from the this relation to find the km. They ask that let's see why we don't use the km expression like this. We had a km for example this type of expression, and the reason is this km is it's an approximation for a stagnant medium, although this is possibly also a stagnant medium. Well, another reason is it's for like it's not just for a stagnant medium, it's for an infinitely larger flat surface. So to derive this equation for this particular problem, we have infinite, well, the number of assumptions. The plate is infinite, and the medium is semi-infinite, and the fluid is stagnant, and it's all under that assumptions. This equation is valid. Now we have a problem which say that the polymer the size is only 2 centimeters squared, and in this case the assumption of that classical problem is broken, so that's why we cannot use that equation. And this is one reason. For some other problems, you may that may be invalid, not because of this infinitely largest place, but maybe because of the fluid is not stagnant, or other reasons. So when you try to like use equations, you need to make sure under what conditions that equation was derived. However, for this mass transfer equation, like the equation we used in the example was basically this one. This equation. This is a very generic equation. There is no any assumption of median being stagnant or not, or the plate. Now the plate size is surface area S. It doesn't tell you that you have to have infinite S. That's not the point. It do allow you to have some surface area S. So we can, for a generic problem, that's why we can use this equation to get started. That's a comment for this one. Okay, so this is the exercise you are going to use. Let's see, what does this equation statement tell us? From a flat liquid surface into stagnant air, the measured mass flux is its coefficient is not be. Well, for this problem, you also don't necessarily need any. Okay, you don't assume the plate either being large or small. You just work from the basic definition of Km. So let me just re-emphasize. So these three equations, equation 1 and equation 2. Well, equation 2 basically comes from equation 1. There's no fundamental difference between these two. And for equation 1, this is generic. This is how the Km mass transfer coefficient is defined. It is defined by a proportionality constant that is between the flux and the concentration difference. Okay, that's the comments I would like to make. Hopefully it helps you to digest further. And now in the special case of this example, like you have a mass transfer, well, from an infinite plate into a semi-infinite. Okay, from a flat plate, this flat plate is infinitely larger. Then for that particular problem, you can derive your Km and delta in this particular way, but it doesn't mean this particular equation is applicable to any other scenarios. All right. That's all for this lecture.